I want to invite you to the casino because in this maths video, gambling is okay. We're looking at the St. Petersburg paradox, okay? This is a paradox about a hypothetical gambling game that I'm going to explain to you right now. It's actually very simple. Everything on the board, I'll explain it in a second, but listen to the rules of this gambling game, okay? You toss a coin over and over and over again until you land on heads, okay? So you might land on heads straight away. You might land on tails and then heads, tails, tails, heads, tails, 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 heads. You keep going until you land on heads. The amount of money that you win at the casino by playing this game is 2 to the power of the number of tosses that it took to get heads, okay? So if I say that capital X is the amount of money that you win by playing this game, you can see that you can win £2 by tossing the coin once, landing on heads. You win 2 to the power of £1, £2, because it only took one toss to get heads. The probability of this happening is 1/2, right? Because you toss the coin, there's a 50% chance that you land on heads. There's a 50% chance that you land on tails. So there is a 50% chance that you land on heads, winning £2. Okay. How would you win £4? That's the next smallest amount of money that you could win. 4 is 2 to the power of 2. So your money gets doubled because it took 2 tosses to get heads. What's the probability of it taking 2 tosses to get heads? Well, you need to first get tails. That's got a 50-50 chance. Then you need to get heads after that. So something that has a 50-50 chance, another independent event that also has a 50-50 chance, that's 0.5 times 0.5, 0.25, or a quarter if you like. Hopefully this game kind of makes sense. Okay, so the 2, 4, 8, 16, this is the possible different amounts of money that you could win by playing the game, right? So if you won £16, that means that you would land on tails, 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 and then heads. It took you 4 tosses to get heads, so you win 2 to the £4, £16. The probability of that happening is 1 in 16. And the same logic applies for any value of X. That's the setup. This is the probability distribution of the game that we're playing, okay? That's the setup of the paradox. I've also written the formula for the expected value of X. That's going to come up in a second. So the question is, how much money should it cost you to begin playing the game? What's the barrier to entry? Obviously, you can't play the game for free. The casino wouldn't like that because you're winning money in every outcome. The smallest amount of money that you can win is £2. You cannot lose money by playing the game. So how is the casino going to profit? Well, they need to charge you a certain amount of money to play the game. It's only fair, right? The question is, how much money should they charge you? Or what's the smallest amount of money that they should charge you so that the casino, at least it's a fair game or it's in the casino's favor, which is typical for a casino. That's the paradox. Because the answer is there is no amount of money that the casino should make you pay to play this game. And you're going to see why right now. So let's work out the average amount of money that you will play, or the expected amount of money that you will make by playing this game in any one situation, in any one time. So how do we do that? Well, we use the expected value formula. The expected value of your winnings is given by this formula. And remember, guys, if you've seen the previous 2 videos on expected values, this is very simple. You multiply each X by the corresponding probability, and then you add them all up. So the expected value of X in this question is 2 times a half, which is the number 1, plus 4 times a quarter, which is also the number 1, plus 8 times an eighth, which is also the number 1, plus 16 times a 16th, which is also the number 1, plus, and then obviously we can see the next one would be 32, and this would be 1 over 32. That's the number 1 as well when you times them. And there's infinitely many, right? Because you could technically get any number of tails before getting heads. So that goes on forever. That's why I've drawn it going off forever. So actually, the expected winnings is 1 plus 1 plus 1 plus 1 plus 1 plus 1 forever. That means the expected value of X, your expected winnings by playing this game in any specific one time, is infinity pounds or infinity dollars. That means that the casino can't ask any finite amount of money from you to enter this game because your expected winnings is infinite. So the casino, mathematically, is going to lose money by allowing this game with any barrier to entry. So this is the paradox. Even if the casino charged you £1 billion to enter this game, mathematically, they will lose money every time someone plays the game on average. Now, that doesn't seem to make any sense because by looking at it and by thinking about the rules of this game, there's a 50-50 chance that you only win £2. So let's say that you do have to pay £1 billion to enter this game. There is a 50-50 chance straight off the bat you're going to lose all of your money or all of your money and then win £2 back. So not basically losing all of your 1 billion. Further, once you've got this 50-50, there is a 1/4 chance that you're also going to lose basically all of your money. There is a 1 in 8 chance as well that you're also going to lose all of your money. And the 1 in 16 chance you're going to lose pretty much all of your money, and so on and so forth. Now, eventually, as these numbers get bigger, I would have to stop saying you're going to lose all of your money because once these numbers get really big, it's actually going to go past $1 billion, right? But who's going to get that? No one's going to get that, right? Because the chances of you winning a massive amount of money, like $1 billion, are so unbelievably slim. And in any one, let's say that it takes you 100 games to do it, right? You've already paid $1 billion, 100 times. So what I'm getting at is no one would play this game. If it cost £1 billion to enter, no one would play this game, even though their expected winnings is a lot more than $1 billion. It's infinite. And so the answer to this paradox, as strange as it is that it's about the utility of the money that you win. So if you're a billionaire and you say, I'm going to play this game for $1 billion, let's say hypothetically that you win money. You probably won't, but let's say that you do. If you double your billion, you might be pretty happy with that. But if you quadruple it, you won't be twice as happy. If you multiply your money by 8, you won't be like 8 times or 4 times as happy or whatever. So the amount of utility or pleasure that you get out of doubling your money each time is not doubling. So that's because people put weight on money in a non-linear way. So it was Bernoulli, one of the Bernoulli brothers, that came up with a kind of answer to this. And there is a solution to the St. Petersburg paradox based on this idea of utility. I won't go through it in this video because it's kind of a separate area of probability, but maybe in the future I will. So in this video, I kind of just wanted to set out what it actually is. It's an interesting example of a game that it's not possible to make it a fair game. If you're familiar with the idea of a fair game, that means the expected winnings in the game is 0. So neither party is expecting to lose money or win money. This is an example of a game that cannot really be made fair because when you play the game, your expected winnings is infinite, which would mean that in order to make it fair, your barrier to entry, the amount of money that you'd have to pay to play the game, is actually infinite as well, which of course doesn't make any sense. So that's why it's called the St. Petersburg paradox, because it is very, very perplexing. But that's the idea. So thank you guys so much for watching. I highly appreciate it, and I'll see you in the next one. Cheers.